Welcome to MasterCode. Episode 9 and the final episode of this series. We've come a long way. From choosing your operating system in Episode 2 through Linux fundamentals, Python for security, web application testing, professional tools, CTF competitions, and bug bounty hunting. Today we close the series by zooming out to the biggest picture, security research. Research is where the knowledge you've built transforms into contribution. Where you stop learning existing techniques and start discovering new ones. Where you go from using tools that researchers made to being the person who makes the tools. This episode is for you if you want to understand how vulnerability research actually works, how to fuzz software and analyze crashes, how to read closed-source binaries, how the CVE process from discovery through responsible disclosure functions, and what career paths are available in security research. We're covering fuzzing, code auditing, reverse engineering, exploit development, the CVE disclosure process, threat intelligence, malware analysis, and the emerging research frontiers that will define the field over the next decade. This is not the end of the series. It's a map of where the series can take you next. Let's finish strong. Responsible disclosure is the ethical framework that makes security research a legitimate and respected profession rather than a criminal activity. Let me explain what it means in practice and why it matters. When a security researcher discovers a vulnerability in software used by millions of people, they hold information that could harm those people if it became public before a fix exists. The responsible action is to give the software vendor time to develop, test, and release a fix before disclosing the vulnerability publicly. This is the coordinated disclosure model. The standard timeline is 90 days, established by Google's Project Zero team based on analysis of what's actually needed to fix complex vulnerabilities. 90 days gives vendors time to identify the root cause, develop a fix, test it for regressions, prepare security advisories, and coordinate release. Vendors sometimes request extensions when they genuinely need more time. These extensions should be granted when the vendor is acting in good faith and making real progress. The exploitation constraint is important during this process. To report a vulnerability, you need to prove it exists. A proof of concept that demonstrates the issue is appropriate. Going beyond that to exfiltrate real user data, maintain persistent access, or compromise additional systems is not appropriate and crosses into criminal territory even when your initial discovery was legitimate. Document everything. Keep time-stamped records of every communication with the vendor. If disclosure becomes contentious, your documentation protects you and demonstrates good faith. The way you handle responsible disclosure determines not just your legal protection but your reputation in the research community, which ultimately determines your career opportunities. Security research is not a monolithic field. It encompasses several distinct specializations that require different skills, different tools, and different career paths. Understanding the distinctions helps you identify where your interests and strengths align with specific research opportunities. Vulnerability research is what most people picture when they think of security research, finding new vulnerabilities in existing software through code auditing, fuzzing, and manual analysis. This is the foundation of offensive security research and connects directly to exploit development and bug bounty hunting. Malware analysis is the opposite end, understanding malicious software created by threat actors. This is primarily defensive work focused on building detections, understanding attacker capabilities, and extracting intelligence from malware campaigns. The demand for skilled malware analysts is extremely high and growing. Protocol research examines the security of communication protocols and cryptographic implementations. Vulnerabilities in protocols affect every implementation simultaneously. Finding a flaw in TLS or a widely used authentication protocol has industry-wide impact. This work requires strong mathematical and cryptographic foundation. Hardware research examines physical devices, IoT products, embedded systems, industrial control systems. Side-channel attacks measure physical properties of hardware operation to extract secrets. Firmware analysis finds vulnerabilities in the software running on microcontrollers. This specialization has unique challenges and relatively few researchers working in it. Academic research drives fundamental advances in security knowledge through peer-reviewed publication. The research cycle is slower, but the ideas have longer-term impact. Fuzzing is the most productive automated vulnerability discovery technique available, and it's responsible for finding thousands of security vulnerabilities in widely used software. Google's Project Zero, which has found some of the most impactful vulnerabilities ever disclosed, uses fuzzing as their primary research tool. Understanding it at a technical level is essential for serious vulnerability research. Traditional random fuzzing sends random data to a program and watches for crashes. It finds obvious bugs but misses the deep logic that only rare code paths reveal. Coverage-guided fuzzing is the modern approach. Tools like AFL++ and libFuzzer instrument the target binary to track which code paths each input exercises. When a mutation of an existing input exercises new code that hasn't been seen before, the fuzzer adds it to its corpus of interesting inputs. This genetic algorithm approach systematically explores the code through combinations of mutations, finding bugs in code paths that random inputs would never reach. The sanitizer combination is critical to making fuzzing effective. Address sanitizer detects heap and stack buffer overflows, use after free bugs, and out-of-bounds reads and writes that would be silent in production builds. Undefined behavior sanitizer detects integer overflow, unaligned access, and other undefined behavior. Compiling your fuzzing target with both sanitizers enabled catches bugs that produce no visible crash in production but indicate genuine memory safety violations. Protocol and API fuzzing extends these concepts to network targets. LLVM sends protocol-compliant but unexpected messages to network services. RESTler generates API requests that conform to an open API specification but contain unexpected values. Let me walk through the AFL++ fuzzing workflow so you understand the practical mechanics of running a fuzzer against a real target. Installing AFL++ is straightforward on Kali. The package includes the fuzzer, companion tools for corpus analysis, and the compiler wrappers. Compiling your target with AFL instrumentation requires replacing the standard compiler with AFL's compiler wrapper. Setting the CC environment variable to AFLCC for C targets and CXX to AFLC++ for C++ targets before running the configure script and make causes all compilation to go through AFL's instrumented compiler. This adds the coverage tracking code that makes the fuzzer effective. The seed corpus is the starting point for your fuzzing run. AFL's genetic algorithm needs valid starting inputs to mutate. A seed corpus of real-world examples of your target format gives the fuzzer a meaningful starting point. If you're fuzzing an XML parser, seed it with real XML files of varying sizes and structures. The AFLFuzz command starts the fuzzer with the input directory, output directory, and the target binary command. The double @ sign is where AFL substitutes the current input file when executing the target. After running for some time, AFL populates the findings directory with crashes and hangs it discovered. Each crash in the crashes subdirectory is a reproduction case that reliably triggers the bug. Reproduce each crash manually first to confirm it's genuine, then analyze it with GDB to understand the root cause. The GDB session shows you the exact instruction that caused the crash and the contents of memory at that point, which is your starting point for understanding what the vulnerability actually is. Code auditing is the manual process of reading source code to find security vulnerabilities through deep understanding of the code's logic and potential edge cases. It requires both security knowledge and programming skill, and it finds vulnerabilities that automated tools miss because they require understanding context and intent. Understanding the architecture before starting is what separates effective audits from random code reading. Read the documentation. Understand what the software does. Identify the most security-critical components: authentication, cryptography, input parsing, privilege management. These high-value areas deserve more attention than utility functions and UI code. Dangerous function search is the traditional starting point for C and C++ code. The strcpy, strcat, sprint, gets, and mempb functions don't check bounds by default. Every call to these functions with user-controlled data is a potential buffer overflow. Search for them, find every call site, and trace whether the input is attacker-controlled and whether the buffer is large enough for all possible inputs. Data flow tracing follows a different approach. Start at the entry points where external data enters the program and trace how that data flows through the codebase until it reaches a dangerous operation. Web frameworks have request parsing entry points. Parsers have file reading functions. Network servers have socket receive calls. These are your starting points. Authentication code deserves the most careful attention because security flaws there have the highest impact. Logic errors in session management, privilege checking, and cryptographic operations frequently create authentication bypasses that are subtle enough to survive code review yet catastrophic in their impact. Error handling paths are systematically under-tested. Reverse engineering of closed-source software is one of the most technically demanding skills in security research and one of the most valuable. Commercial software, firmware in embedded devices, and malware all require analysis without source code access. The fundamental approach combines static analysis of the binary structure with dynamic analysis of its runtime behavior. Ghidra's decompiler is the starting point for most closed-source binary analysis. It converts the assembly instructions of the compiled binary back into approximate C code that represents the program's logic. This pseudo-C is not identical to the original source, but it's readable and analyzable. Navigate to functions of interest based on string references, imported function calls, or behavioral indicators from dynamic analysis. The decompiler output tells you the algorithm the function implements and where it gets its inputs. Dynamic analysis with GDB or the Windows equivalent x64DBG provides information that static analysis cannot. Running the binary under debugger control lets you set breakpoints at interesting points, inspect memory contents in real time, trace execution paths, and observe the actual values of variables during program operation. This is particularly valuable when static analysis reveals complex logic that's difficult to reason about without seeing actual inputs and outputs. The combination is essential. Static analysis gives you the structural understanding, which functions exist, what they call, what the overall program flow looks like. Dynamic analysis gives you the runtime context, what values actually appear in memory, which code paths execute for specific inputs, and where the program's behavior diverges from what static analysis suggested. QEMU emulation extends your capability. Let me walk through the practical Ghidra and firmware analysis workflow that researchers use on real targets. Ghidra's headless mode allows automated analysis without opening the GUI, which is valuable for processing large numbers of binaries or integrating analysis into automated pipelines. The analyze headless command takes a project directory, project name, and the binary to import and analyze. Post-processing scripts can then query the analysis results programmatically. For interactive analysis in the Ghidra GUI, the workflow is consistent. Import the binary through the File Import menu. Ghidra automatically detects the architecture and file format for most standard executable formats including ELF, PE, Mach-O, and raw firmware blobs with manual architecture specification. The auto-analysis phase applies disassembly, decompilation, and various heuristics to build the initial analysis database. Searching for strings reveals the binary's plaintext data, which often includes error messages, configuration parameters, and sometimes credentials or cryptographic keys. Firmware analysis with binwalk is a separate discipline that precedes Ghidra analysis. Embedded device firmware is typically a compressed file system containing multiple binaries. Binwalk signature detection identifies embedded file systems, compressed archives, and executable code within the firmware blob. The extract flag automatically decompresses and extracts the identified components. The resulting directory tree contains the device's file system with all its configuration files, executable binaries, shell scripts, and web interfaces. Searching this file system for hard-coded credentials, default passwords, and private keys is basic but consistently productive. Exploit development is the discipline of taking a confirmed vulnerability and building reliable code that exploits it to achieve a specific security impact. This is one of the most technically demanding areas in security research, and the skills command the highest compensation in the field. Memory corruption vulnerabilities, the classic category including buffer overflows, use after free, and heap corruption, form the foundation of exploit development knowledge. Understanding how memory is organized and processes, how the stack and heap work, and how function calls manage return addresses is the prerequisite for anything more advanced. Return-oriented programming, or ROP, is the technique that makes exploitation viable on modern systems with non-executable memory protections. Instead of injecting shellcode that runs directly, ROP chains together small sequences of existing code from the binary's own code called gadgets, each ending in a return instruction, to perform arbitrary computation without injecting new code. The heap exploitation field has become enormously complex as browser vendors and operating system developers have invested in heap hardening. Techniques like cache poisoning in glibc, house of bot cake, and various chunk corruption methods require deep understanding of allocator internals to apply correctly. Kernel exploitation targets vulnerabilities in the operating system kernel itself, which runs with the highest privilege level on the system. Exploiting a kernel vulnerability typically provides complete system compromise. The attack surface includes device drivers, file system implementations, network stacks, and core kernel data structures. Browser security research involves the JavaScript engine internals, the JIT compiler that dynamically compiles JavaScript to machine code, and the multiprocess sandbox model. JIT compiler vulnerability. The CVE process is how newly discovered vulnerabilities become part of the public record that defenders use to prioritize patching and researchers use to track vulnerability trends. Understanding it helps you handle your own discoveries professionally. When you discover a vulnerability, your first action should be thorough documentation. Write a clear description of the vulnerability that includes what software is affected, what versions are vulnerable, what conditions are required for exploitation, what the impact of successful exploitation is, and the steps to reproduce it. This documentation serves as both your disclosure report to the vendor and the basis for your CVE submission. Finding the vendor's security contact requires some research. Many organizations publish a security.txt file at the well-known path/security.txt that lists the correct contact. Many have a security@domain email address. CERT organizations like the US CERT and international equivalents serve as intermediaries when direct contact isn't possible or when vendors are unresponsive. Use encrypted communication when possible. PGP encryption for email communications protects the disclosure from interception during the coordinated disclosure window. Once contact is established, share your documentation and agree on a disclosure timeline. The standard 90-day window starts from the date of vendor notification, not from when you discovered the vulnerability. During this period, the vendor develops and tests a fix. Your role is to answer technical questions that help them understand the vulnerability and verify their fix works. After 90 days, public disclosure happens regardless of patch status. This policy protects users by ensuring that vendor delays don't leave systems indefinitely vulnerable without public awareness. CVE assignment can be requested to. The research toolkit extends well beyond the penetration testing tools we've covered in previous episodes. Let me introduce the tools that researchers use for deeper analysis and systematic vulnerability discovery. CodeQL is a semantic code analysis engine developed by GitHub. It lets you write queries that express vulnerability patterns and run them against codebases to find all instances of that pattern automatically. A query that finds all places where user-controlled data flows into a SQL query without parameterization, for example, applied to a large codebase, finds every potential SQL injection point. Anger is a Python framework for binary analysis combining static analysis, dynamic symbolic execution, and constraint solving. Symbolic execution explores all possible program paths simultaneously using mathematical variables rather than concrete values. When it reaches a condition, it computes what input values would be needed to satisfy each branch. This makes Anger powerful for finding what input values trigger specific program states, including crash conditions. SemGrep performs lightweight static analysis using pattern matching rules. It's faster and simpler than CodeQL but less powerful for complex data flow queries. For common vulnerability patterns in source code, SemGrep scans large codebases in seconds. The community maintains rule sets for common languages and vulnerability categories. Valgrind's memcheck tool instruments program execution to detect memory errors including invalid memory accesses, use of uninitialized memory, and memory leaks. Running your fuzz corpus through Valgrind memcheck catches bugs that don't crash the normal process but indicate memory safety violations. TestCell and Slice analyze TLS implementation quality. Threat intelligence research tracks real adversaries, their capabilities, and their activities to provide defenders with actionable intelligence about current threats. This work requires combining technical analysis skills with investigative methodology. Ascent on threat actors involves monitoring the channels where they communicate. Cybercriminal forums on dark web markets, Telegram channels where threat actors sell tools and share techniques, and public social media where nation-state affiliated groups sometimes leak operational information. This monitoring requires appropriate tools and safe operational practices since the sources can themselves be adversarial. Malware sample analysis produces the technical intelligence that feeds into detections and incident response. Services like Any.Run and VirusTotal provide cloud-based analysis environments where you can safely execute samples and observe their behavior. Cuckoo Sandbox allows you to run your own controlled analysis environment for samples that you don't want to send to cloud services. Dynamic analysis reveals C2 communication patterns, file system artifacts, registry modifications, and process injection techniques that form the behavioral signature of the malware family. MITRE ATT and CK is the standard framework for describing and categorizing adversary tactics, techniques, and procedures. When you analyze malware or respond to an incident, mapping observed behaviors to ATT and CK techniques produces structured intelligence that communicates precisely what the attacker did. This structured format enables comparison across incidents, attribution analysis, and defensive coverage assessment. Indicator extraction produces the concrete artifacts that enable detection, IP addresses and domains used for C2, file hashes of malware samples, array signatures that match malware byte patterns. Security research careers offer three distinct paths with genuinely different trade-offs. Understanding these helps you make intentional choices rather than drifting into one by accident. Industry research positions at major technology companies offer the highest total compensation. Google Project Zero, Microsoft Security Response Center, Apple's Security Engineering Team, and similar organizations provide excellent resources, collaboration with talented colleagues, and real-world impact through fixing vulnerabilities in widely deployed software. The trade-off is that most research is constrained by the company's interests and many findings are kept internal under NDA rather than published publicly. Academic research provides complete intellectual freedom. You choose your research questions, publish all findings, and collaborate globally with other researchers. PhD programs provide deep expertise development and access to other academic researchers at the frontier of the field. The compensation is significantly lower than industry and funding pressure through grants creates its own constraints. The academic path is most appropriate for researchers who want to work on fundamental problems rather than applied vulnerability finding. Independent research combines freedom and variable income. Bug bounty hunting, consulting engagements, and paid research from security vendors all provide revenue streams. Building a public research portfolio through conference presentations and blog posts creates a brand that commands consulting fees and speaking opportunities. The isolation risk is real. Working alone without colleagues to review ideas or share tools can slow development. Many successful independent researchers maintain community connections that offset this. Career paths aren't permanent. Researchers commonly move between industry, academia. Malware analysis is a discipline that requires both technical depth and systematic methodology. The goal is to understand what a piece of malicious software does, how it evades detection, and what artifacts it leaves that can be used for detection and response. Static analysis before execution gives you information that doesn't require running the sample, which is important because malware can behave differently in analysis environments than in real ones. The file command and PE header analysis reveal architecture, compilation tool chain, and sometimes packer signatures. Checking the sample hash on VirusTotal reveals whether the sample is known and what other research exists on it. Strings output and import table analysis reveal network indicators, file paths, and functional capabilities from the APIs the malware imports. Dynamic analysis in a controlled sandbox gives you the behavioral record. Any.Run's interactive analysis lets you interact with the sample in real time while it records all system calls, network connections, file operations, and registry changes. Cuckoo produces automated behavioral reports. LLVM on an isolated Windows virtual machine lets you manually analyze samples in a controlled environment with the full set of Windows malware analysis tools. Unpacking is often required before meaningful analysis is possible. Modern malware uses commercial packers or custom code to compress and encrypt the real payload and only decompress it in memory at runtime. Dynamic analysis with x64dbg allows you to run the packer, set a breakpoint when the packed payload is decompressed in memory, and dump the unpacked executable for GIDRA analysis. C2 infrastructure analysis follows the network indicators to understand how the malware communicates with its operators. DNS resolution history, certificate. YRA is the standard tool for creating signature-based malware detection rules that work across security products, threat intelligence platforms, and incident response tools. Writing effective YRA rules is a skill that produces concrete defensive value from your malware analysis research. YRA rules match files based on byte patterns, regular expressions, and logical conditions combining multiple matches. A rule specifies the strings it looks for and the condition that must be true for the rule to trigger. The metadata section provides human-readable context about what the rule detects, who wrote it, and when. Strings in a YARA rule can be text strings, hexadecimal byte patterns, or regular expressions. Text strings match exact text with optional modifiers like no-case for case-insensitive matching and wide for UTF-16 encoding. Hexadecimal patterns match specific byte sequences and support wildcards with question marks and ranges for variable bytes. Regular expressions use PCRE syntax for flexible pattern matching. The Bitcoin address pattern in the example uses a regular expression that matches the format of a Bitcoin address, which appears in ransomware that specifies payment destinations. The condition determines when the rule triggers. The any of them condition triggers when any string in the strings section matches, which is appropriate for a rule that detects multiple independent indicators. You can also specify that all strings must match, that a minimum number must match, or create complex Boolean combinations. Testing your rules against known malicious samples and known clean files before deploying them validates that they catch what they should and don't produce false positives. VirusTotal Intelligence allows you to search for files matching your YRA rule across their enormous malware database, which is invaluable for finding. The security research community is one of the most collaborative and knowledge-sharing communities in any technical field. Engaging with it actively accelerates your development and creates opportunities that isolated learning cannot provide. Writing and publishing your research is the most important community contribution you can make. A well-written blog post explaining a technique you mastered, a vulnerability class you analyzed, or a tool you built reaches people who need exactly that knowledge and positions you as someone who contributes rather than only consumes. Start writing even before you feel like an expert. The act of explaining something to others clarifies your own understanding and consistently reveals gaps. Conference presentations at DEF CON, Black Hat, and their regional B-sides equivalents are the highest visibility form of research sharing. DEF CON's call for papers is highly competitive and submission quality needs to be strong. Local B-sides conferences are much more accessible for first-time speakers, and some of the best security content I've encountered came from B-sides presentations by researchers sharing their first discoveries. Submitting to local events first builds your presentation skills and gets your research in front of an audience before the larger venues. Open source contribution creates lasting community value. A tool you write and release publicly, detections you submit to open rule sets, or documentation improvements to existing projects all compound over time as other researchers build on them. Contributing to projects you use builds connections with the core developers and demonstrates your technical capability through code rather than words. Research groups and Discord communities focused on specific research areas provide peer review that isolated work can't get. Having other researchers challenge your assumptions, suggest alternative approaches, and identify gaps in your analysis produces significantly better work. The security research frontier is moving rapidly into new domains that traditional security expertise doesn't fully cover. Understanding these emerging areas helps you identify where to specialize for maximum impact over the next decade. AI and large language model security is the most rapidly expanding research area right now. Prompt injection attacks manipulate model behavior by embedding instructions in user input that the model treats as system commands. Training data extraction attempts to recover sensitive information that appeared in training data. Model inversion reconstructs training examples from model outputs. Jailbreaking techniques bypass safety constraints. These attack classes are new enough that there's no established research consensus on their severity or mitigations. Researchers with both ML knowledge and security background are exceptionally well positioned here. Cloud-native security research focuses on the infrastructure layer where modern applications run. Kubernetes misconfiguration, container escape vulnerabilities, cloud service API issues, and IAM policy analysis are where most enterprise security incidents originate. The tools and techniques are still being developed by the community. Software supply chain security emerged as a critical concern after high-profile attacks demonstrated that compromising one supplier can propagate malware through thousands of downstream users. Analyzing build systems, dependency management, code signing infrastructure, and update mechanisms for systematic vulnerabilities is a growing research area. Hardware security research continues to produce surprising results. The discovery that CPU microarchitectural features like speculative execution could be exploited for information disclosure, demonstrated by Spectre and Meltdown, opened a research area that remains active. Cache timing certifications in security research serve different purposes at different career stages and for different types of employers. Understanding this helps you make strategic decisions about where to invest your time and money. OSCP, the Offensive Security Certified Professional, is the most widely respected hands-on penetration testing certification in the industry. The exam is purely practical. You're given access to a network and required to compromise a set of machines within 24 hours using only your own knowledge and tools. No multiple choice questions. No memorization. Pure applied skill. Technical hiring managers at security companies universally recognize OSCP as meaningful validation of practical penetration testing ability. It's the right certification to pursue first if you're heading toward professional penetration testing work. OST covers Windows exploit development and is designed for researchers who want to specialize in exploitation. The curriculum includes shell coding, SCH-based exploit development, and ASLR bypass techniques. This certification is the right choice for people heading toward vulnerability research and offensive security engineering roles. GREM from GIAC validates malware analysis and reverse engineering skills. It's the standard certification for malware analyst positions at security vendors, threat intelligence companies, and incident response teams. If malware analysis is your target specialization, GREM on your resume signals appropriate expertise to technical hiring managers. The practical reality is that certifications validate for human resources departments and non-technical hiring managers more than for technical ones. A researcher with published CVEs, conference presentations, and an active GitHub repository of tools will be evaluated primarily. Setting up your research environment properly from the start saves significant time and prevents the amateur mistake of doing serious research on a machine that's vulnerable or insufficiently isolated. A dedicated research virtual machine separate from your daily computing environment is the foundation. Malware analysis in particular requires careful isolation because samples can attempt to spread, exfiltrate data, or detect analysis environments and behave differently. Your research VM should have no access to real user accounts, no access to sensitive data, and network isolation that prevents accidental propagation. Installing Ghidra, Puntools, and AFL++ gives you the core research toolkit for reverse engineering, exploit development, and fuzzing respectively. Add Binary Ninja or IDA Free for alternative perspectives on binaries that Ghidra's decompiler struggles with. Each decompiler has different strengths and weaknesses on different code patterns. Having multiple available means you switch to a different tool when one produces unclear output. The fuzzing environment requires careful setup because fuzzing involves compiling targets with instrumentation and running them at high throughput. Create a dedicated directory for each fuzzing project with the instrumented target binary, seed corpus, and findings directory clearly organized. Network analysis infrastructure should include both live capture capability with Wireshark and TCP/dump for ongoing monitoring and offline analysis capability for PCAP files from research targets. Zeek, formerly known as Bro, converts raw packet captures into high-level protocol logs that make pattern analysis much faster than full packet analysis. LLVM from Mandiant is a Windows-based malware analysis environment that installs a comprehensive toolkit through a single PowerShell script. It includes disassemblers. The security research resources I'm listing here are the actual sources that working researchers use to stay current and to build deep knowledge. These are not sponsored recommendations. They're what the community actually reads and references. Google Project Zero's blog represents the highest quality public vulnerability research available from any source. Their researchers consistently find and disclose vulnerabilities in the most security-sensitive software, including browsers, operating systems, and cryptographic libraries. The analysis quality in their posts is exceptional. They explain not just what the vulnerability is but how they found it, how they analyzed it, and what the root cause reveals about the broader security of the codebase. DEF CON's media archive contains recordings of every talk given at DEF CON since the early 1990s. Decades of security research from the most innovative minds in the community, available for free download. Browsing by year reveals how the field has evolved. Specific technical areas like wireless security, web security, and hardware hacking have rich talk archives that constitute a complete course on each subject. ExploitDB contains the actual exploit code for publicly disclosed vulnerabilities. Reading exploit code rather than just descriptions is dramatically more educational. Understanding how a vulnerability is exploited, what preconditions it requires, and how the exploit handles reliability challenges builds exploitation intuition that abstract descriptions cannot provide. AR14's computer security section publishes academic papers before peer review, making cutting-edge research available months before journal publication. The quality varies more than peer-reviewed venues, but the pace is significantly faster and the research often represents the most current thinking on emerging security problems. We've reached the final slide of the final episode of this series, and I want to say something directly to you. You started this series as someone who wanted to learn security. If you followed this series from episode 2 through to here, you are not that person anymore. You've covered operating systems, Linux fundamentals, Python programming for security, web application vulnerability classes and testing methodology, professional tools and engagement workflows, CTF competition strategy and technique, bug bounty hunting methodology and report writing, and now security research fundamentals. That's a genuine foundation. Not a complete career, but a foundation that took many professionals years to build through trial and error. The path forward from here requires practice. Every topic in this series converts from knowledge into skill only through application. CTF machines that you struggle through. Bug bounty reports that get rejected and teach you what better looks like. Code that you audit and the vulnerability that you find when your methodology is systematic enough. Research that you publish and the community feedback that sharpens your thinking. Specialization should be deliberate. The generalist foundation you've built is valuable, and it's also the beginning rather than the destination. Pick the area where your interest is strongest, where the market rewards the skill, and where your background gives you a natural advantage. Go deep in that area consistently for the next 12 months. The security community is one of the most genuinely collaborative communities in any technical field. The researchers who have contributed the most to public knowledge are the ones with the strongest reputations and the most opportunities. Contribute. Share what you learn. Help people who are where you were 6 months ago. The field advances through this chain of shared knowledge. And that's the Complete from Zero to Hacker series. 9 episodes covering everything from choosing your operating system to conducting original security research. The knowledge is real. The techniques are the same ones that professional penetration testers, CTF winners, bug bounty hunters, and security researchers use in real work every day. Here's where you go from here. Pick one thing from this series that you haven't practiced yet and practice it this week. Not next month. This week. Open Hack the Box and solve a machine. Submit a bug bounty report. Write a fuzzing harness. Publish a blog post about something you learned. One concrete action converts all of this knowledge from something you've watched into something you've done. This channel is continuing. We're going deeper on specific topics, covering new developments as they emerge, and building toward more advanced content that extends from the foundation we've built together. Subscribe so you catch every new video when it drops. And if this series gave you genuine value, if it taught you real things that you can apply, sharing it with one person who would benefit from it costs you nothing and might change their trajectory. Thank you for watching. Thank you for being part of the MasterCode community. The knowledge is yours now. Go use it.